Hello everyone. Today we'll talk about the solution to the problem minimum total distance traveled. This problem is a variation of a classic problem where we have on a line some two types of objects, let's say circles and triangles. We want to assign every circle to some triangle, and every triangle can have at most one circle assigned, in such a way that the sum of distances between elements of every pair, between a circle and its associated triangle, that's the sum of those is minimized. And the trick in this problem is that there can be more triangles than circles. Because this basic version, where there are exactly the same number of circles and triangles, can be solved greedily. But this problem, where some triangles may be unassigned, and of course they can be multiple triangles in a single spot, is more difficult because we don't know a priori which triangles are to be used and which ones are not used. As it turns out, in this case the problem becomes a bit harder, and I don't think a linear or n log n solution is feasible here. So we have to think about something slower than that. So we know that greedy doesn't work, and what do we think about when greedy doesn't work? It's pretty natural to think about dynamic programming. And for dynamic programming, we have to have a notion of a smaller subproblem and a way of combining solutions to smaller subproblems into the solution for a larger problem. In this case, what we can consider is we can consider only some set of robots and some set of factories. And even more conveniently, we can consider some prefix, so some first X robots from the left and first X factories from the left. And if we can, using solutions calculated for a smaller prefix, either of robots or factories, to get a solution for a larger one, we can finally end up with all the robots and all the factories. Because it's easy to notice that in any optimal solution, we indeed want to assign first robots to some first set of factories. In particular, it doesn't make sense for two robots to cross over each other, because otherwise we can just swap their factories, the crossover disappears, and the total distance travel will probably become smaller. Well, it has to become smaller because there is no point in for two robots to cross over each other. And that means that we can either use tabularization or memoization to remember the solution for some prefix of robots and factories and use that to solve the problem. We can of course explicitly think about prefixes. We can also think about suffixes. This is all just implementation details. The first thing we have to do then is to sort our robots and factories, because we want to be considering only some first robots from the left, some first factories from the left. And now we'll be using, for memoization, the standard Python cache decorator from functools. And we want to be able to calculate the result for first R robots and first F factories. And since in this problem factories have some capacity, we can either transform the list of factories into an expanded list where every factory has capacity 1 and appears multiple times, or we can remember how many robots were already using this factory. I opted of course for the second option, as you can see. The base cases are simple. If no more robots remain to be repaired, we have to pay 0 to repair all the remaining robots. Otherwise, there are some robots to be repaired, but there are no more factories. We have some infinity, some century value to make sure that this is impossible to reach. That century value for me is 10 to the 14th. You can just look at the problem constraints to come up with a big enough value that's bigger than any proper solution to the problem. And now we can either skip the factory, this is always possible, because we'll be generating all the options for our decision here and taking the minimum over all the options. So you can either skip this factory, so the answer is the answer for first R robots, the next factory, and that next factory hasn't been used at all. Or we can try to use that factory if it has some remaining capacity. If it has remaining capacity, we'll have to pay the distance between the RF robot and the F factory. And then, since the RF robot is already covered, we can add to that the answer for the next robot, and the same factory with one more spot used up. Those are the two options. We want to return the minimum of those options, And of course we start with 0 robots, with the 0 factory, 0th robot, and no robot has used any capacity in that factory. So this is a memoized recursive solution to this problem. It would be probably faster to use a tabularized solution if you prefer that, or if you want to test your understanding of this solution, then feel free to do so on your own.